Okay, so now let's consider observer O again and the future light cone of O, and this is the past light cone. And let's consider a space-time point which is located at some xa and some time ta within the future light cone. Okay, and let's ask, if we take the observer O, who is sitting at 0, 0, let's ask, what is the space-time interval between these two space-time points? That is the space-time point A, which is within the future light cone, and the space-time point O. And that space-time interval is just c times ta minus 0 square minus xa minus 0 square. And since the y and z coordinates are the same, we need to choose them to be the same to represent this diagram. Those two space-time points, the y and z coordinates don't contribute anything to the space-time interval. Okay, so this space-time interval we should really think as a measure of distance between these two space-time points. And the reason why we should think of it as a measure of distance is because if we take a different inertial observer who is moving with respect to our observer or our frame S, in which we've labeled these space-time points, that different observer would also measure the same distance or the same space-time interval between the points O, the space-time point O and the space-time point A. So a different observer might have a different labeling for the point, for the space-time point at O, and a different labeling for the space-time point at A. But they will agree with the observers in frame S about the space-time interval between these two space-time points. And in fact, every single inertial observer, no matter what their labeling of the space-time point O and the space-time point A is, will agree, okay, on the value of that space-time interval. So the space-time interval is really some kind of measure of distance between space-time points. Now, this measure of distance is different from the measure of distance that we use in Euclidean geometry in a couple of different ways. One is that this distance measure is not positive. Okay, so this distance measure can be positive, it can be negative, it can be 0. And so now if I compare with the Euclidean distance measure, that is, if I just look at the sheet of paper and I just draw the line connecting O with A, okay, so on the sheet of paper, this distance is xa, and this distance is cta. So this distance from here to this point, okay, if I just take a ruler and hold it up against this distance, what I would measure by the Pythagoras theorem would be cta square plus xa square. Okay, this distance measure is not the physical distance between space-time points. This is just the representational distance on our sheet of paper. So this distance measure, or this length as we've drawn on the sheet of paper, has no physical meaning as the distance between the space-time points. The physical distance between the space-time points is the space-time interval, okay, which is this quantity, cta square minus xa square. Different observers will agree on the value of the space-time interval, but they will not agree about the value of this quantity. Okay, so therefore this quantity is not a sensible measure of the space-time distance between two spatial points. That is only a length on our sheet of paper where we're representing these space-time points. Okay, so this distance measure is called a distance measure of Minkowski spacetime, which is different from a distance measure on what we call Euclidean space, where Pythagoras' theorem holds. Okay, so I'm going to erase this now. Now, let's ask an interesting question. In Euclidean space, if we take a point O and we ask what are the points that are equidistant from this point, that is, what are all the points in space which are equidistant from this point, we would get a circle surrounding O. Okay, and all these points would be at the same distance r. Now we can ask, in this Minkowski spacetime, or with the Minkowski distance measure, what is the set of all points that have the same distance, or what is the set of all spacetime points that have the same spacetime distance from O? So if we take this point, CTA XA, and we take its distance measure from O, we can now ask what other spacetime points have exactly the same spacetime interval between them and O. Okay, and so what we're asking is, if we take another point at a time t and at location x, what we're asking is, what is the set of all points that have ct square minus x square equals constant? Now, if you insist that this set of all points passes through CTA comma XA, this fixes the value of that constant. And the other thing is, now you know what this curve is, okay? This curve is a hyperbola with asymptotes CT minus x equals 0 and CT plus x equal to. Okay, in other words, those asymptotes are nothing but the light cone. Okay, because this future light cone, this light beam which propagates outwards from O, has an equation CT minus x is equal to 0, and this light beam which propagates from O in the negative x direction has an equation CT plus x is equal to 0, which describes it. Okay, so the set of all points that have the space-time distance or space-time interval from O the same as that of the point CTA comma XA are points that pass through CTA comma XA. It's a hyperbola that passes through CTA comma XA, and it has asymptotes which are on this light cone. Okay, so that set of all space-time points we can now draw, and it would look something like this. Okay, where I haven't shown it all the way, but you can imagine that this hyperbola asymptotes, okay, to the light cone. Now, if you look at this hyperbola, you see that there's a point over here, which I will point out over here, which corresponds to a space-time point which is at the same spatial location as O, but is at a future time. So this is at the spatial location 0, but let's say it's at a time tau. Okay, So for this point as well, it should be true that c tau square minus 0 square is equal to the same spacetime interval, okay? Or is equal to c times ta square minus xa square. So in other words, that spacetime interval that we had evaluated earlier in terms of CTA and XA should be equal to C times tau square. And obviously this quantity is positive. Okay, so this is positive. And the other thing that you would notice is that this time tau is measured on a clock that is stationary, that is, it stays at the same location O. So this time tau is also what we would call the proper time. Of O. Okay. So the space-time interval of all these points can be measured by just looking at the clock at this instant of time at O's location. Now, if we consider a second space-time point, which is, say, over here, so with a value of tau which is smaller than the value of tau over here, so this clock is still at O's location, but has a value tau prime which is less than tau. And we consider the set of all space-time points that pass through, that have the same distance from O as the point C tau prime comma 0. We would again get a hyperbola, and this hyperbola would look like this. Okay. So the set of all space-time points that are equidistant from O, using our notion of a space-time interval defined by this Minkowski measure of space-time distance, all such points trace out hyperbolas. Okay, so we get many hyperbolas, and all points on this green hyperbola are equidistant from O. All points on this magenta hyperbola are equidistant from O, and all points on the orange hyperbola are also equidistant from O. And the other important point is that for all points inside this future light cone, or all these hyperbolas inside the future light cone, write this down, for all space-time points inside the future light cone, we would have the space-time interval between any point here, P. Okay, you can always draw the hyperbola of that point P. It would always pass through a point which is just located at the same spatial location at O, but at a future time. And therefore, the space-time interval would be of this form. It would be C times whatever time tau you have over here. In this case, it would be tau prime square. Okay, that would be the space-time interval, and that would be positive. So for all space-time points inside the future light cone, the space-time interval is positive. Now, we say that such points are time-like separated from O because the space-time interval to the point P and the space-time interval to the point C tau prime 0 are the same, and the points c tau prime 0 or c tau 0, these points are separated from O as if they were just clocks which were located at the same location as O, but you just waited to see what their time was in the future. Okay, and so such points are time-like separated. We say that all such points are time-like separated. So the point P is also said to be time-like separated because its space-time interval is positive. It's similar to what a clock just sitting at O would do, okay, in terms of its space-time distance from O changing.